started. Today, we're finishing chapter 2. Today's the 5th. This has been changed to reflect, the day off action. And then next week is chapter 3, and your second quiz is on the 14th. All right? Tim, you sure? All right, let's get started with this. Let's see here. 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 How do you feel about graphing constraints? Do you feel good about it? If you feel really good about it, you don't have to take notes. If you don't, maybe you should take notes because this is like a quick review right here. Objective function, 3 constraints. I'm going to start with the top constraint. I'm going to set my x1 to 0, solve for x2 to get the coordinate, and then I'll set x2 to 0 and solve for x1. This is all reviewed, so that's why it sounds like it's going a little fast. You ready? Right here. I'm going to turn x1 into 0, so that leaves me with 5x2. I'm turning all these into equals. Equals 10. I'll divide both sides by 5. x2 equals 2. Is that correct? Yes. So the coordinate here would be 0, 2. x1, when x1 is 0 for this constraint, x2 is 2. Now I'm going to make x2 0 and get the coordinate with x1. What did I say? Okay, 2x1 equals 10. I divide both sides by 2. X1 equals 5. This coordinate would be 5, 0. So there's the first constraint. There is where it crosses the axis. And now I can graph it, extend my line, put the arrows, and we'll go to the second constraint now. Right up here, making x1 0, it leaves negative x2 equals 12. Is that right? Okay. We multiply each side by -1 or divide by -1, whichever the case may be. x2 equals negative 12. So this one, what? I don't feel confident on this one. I got to stare at it for a second. Yeah, that's right. So this one would be 0, negative 12. Thank you. Now I'm going to make x2 0 and solve for x1. So I get 4x1 equals 12. Divide both sides by 4. I get x1 equals 3. This ends up being 3, 0. Here are the coordinates where the second constraint would cross the axis. I would connect those coordinates. I would extend the line. I'm going to have to, someone have a big straight edge or something we can use to straight edge. Maybe that folder would be unfolded or something. Third one, right here. I'm making each of them 0. There's no numbers with them. I'm going to the express route on this. If I make that 0, it's x2 equals 4. If I make the other one 0, it's x1 equals 4. Right? Everyone know? So this is going to be 4, 0, 0, 4. Okay? There's my coordinates for the constraints. And now I'm going to graph the constraints. Here's the hard part, for me at least, because I don't have a straight edge. This is going to be awful. What's my largest number? I do these first so I know what my largest number is. I got to make sure it's on the graph, which is the negative 12. And then the other largest number on the x, as far as positive, we have a 4, a 5, thank you. The other x, we have a 4, a negative 12, and a 2. So the reason I'm making this into dots, because usually we don't need the coordinates, the axes that are out here in this area. Our answer is right here. For this whole semester, the variables will always be 0 or greater, which represents this coordinate area, or this area right there. Let's see, I gotta make sure I do this. So if negative 12 is way down here, negative 12, I gotta make this equal, so I gotta go about the same distance up here. What do you think? About right here? Okay, make that a positive 12. Now I can kind of scope on this and go, well, that would be a 6. I'm going to go this way. Okay, I got to extend this. So this would be about, does this look okay? 12. There's only one person answering. 6. I went a little. 3. 9. This is how I do it to make sure it kind of, everything's even. We look okay so far? Ready? What happened?
The 6 is kind of off.
Is it? It's not between the two?
No.
Oh, this one.
Yeah, that one.
Yeah, that's way off. Thank you.
There you go.
How's that?
That's better.
All right. 0, 2, 5, 0. Here's the first one. 0, 2, now I gotta go up a little, about right there, and 5, 0, go about right there, gotta have straight edge, because this one, to be able to determine where the optimal solution is, these lines are so close together, if you don't do it right, you're gonna miss it. That's too much of a hint, I just gave you, what's about to happen. Here we go. Not bad. Okay, there's that one. See, I wanted to make that solid though, so that's not good. 0, negative 12, which we did this on purpose right here. 3, 0, is that right here? Okay, now I gotta make sure and extend this. So, okay, here's the hard part. I want to make sure it extends out in here. This part doesn't matter. Here. Okay, this part matters. The last one's 4004. Well, here it is, right here. Gotta make sure. All right, there and there. Oh, man. You see what's about to happen?
Yeah.
Okay, right there. Look at this. Everybody see it? I may have made a mistake. I can see from here I did. Darn, what did I make a mistake in?
Telling the department trip that we rule again.
0250 is 0250. Where is that? Is this it right here? This one right here. I'm going to pick a point on either side of this line to determine which way the shading should go. My favorite point I like to pick is which?
0, 0.
No. 1, 1. 1, 1's on this side. If 1, 1 fits the constraint, that's the side I will shade. If not, I'll shade the other direction. Throwing a 1 in there. 2 times 1 is 2. 5 times 1 is 5. 5 plus 2 is 7. Is 7 greater than 10? So I must shade the other way, the opposite way. From this line, now I want to make sure, see I don't know where, so I'm just lightly, because to make sure I know which direction I'm going here. There we go. There's something wrong here. Where are we at? Next one is the 12, negative 12, so that's this line right here. I'm going to pick a point on either side, plug it in, see if it makes sense. I'm going with 1, 1. 4 times 1 is 1. 1 minus 1 is, I'm sorry, 4. 4 minus 1 is 3. Is 3 greater than equal to 12? So I'm not shading that direction. I have to shade this direction. The last one is this line right here. This is this constraint. I'm going with my favorite point, 1, 1. 1 plus 1 is 2, greater than equal to 4. You say no. That means I'm not shading where 1, 1 is. I'm going to shade the opposite way. This is this line right here. Now, I now have to stare at it and say, where are all shades crossing? Not just 2 of the shades. Where do all the shades cross? And where all the shades cross is called what? That area is called what? Where all the shades cross? No, say it again.
Feasible range.
Feasible region. Feasible region. Second thing in our list there is feasible region you will have to identify on the upcoming quiz. It's where all of them. If this is going this way, and this is going this way, and that's going that way, right here is the shading. This has all 3 shades. I'm going to kind of darken this whole thing. Now my mistake is this line right here, I made too far to the right. That's why I needed a straight edge. It's got to be over here. There should be 2 extreme points here. There's only 1. Do you get what I did so far though? All right. I'm going to pretend there's a point there, and another point right here crossing 2 lines, touching the feasible region, crossing 2 lines, touching the feasible region, crossing 2 lines, touching the feasible region. And that's all I see as far as where lines are crossing, touching the feasible region. So that tells me those points are called the extreme points. And in this case, there's how many extreme points? 3. All right? One of those 3 points is your optimal solution. Now I could figure out where each point's at. This one would be especially easy right here. That would be, is that 4 or 5? 5, 0. So we got that point, 5 comma 0, and we can plug that in. 5 times 5 is 25, 25 plus 0 is 25. We're trying to minimize. Now I could figure out what that point and that point is, and plug it in, and do the math also. Then whichever one of the three gives us, finish this sentence, gives us the blank amount that our optimal solution, what's the blank? The lowest amount, because it's a minimization problem, whichever one. And that, it used to be a way everybody would kind of solve this a little bit. Find those points and plug them in, whichever one gives us the minimization is our optimal solution. Now, using the graphing method, though, we can graph the objective function and figure out where it would be touching, which extreme point it would be touching, as it's just either entering or leaving the feasible region, whichever way you go. All right? So obviously there's going to be an objective function line, and it's going to be either, as it's, depending on its angle, where would it be touching the feasible region, and only at one of these spots. There's one of these spots. So, how do we graph 5x1 plus 2x2? We set it equal to any arbitrary number you want to pick out of the air. It does not matter. Everybody can have a different number. I like to go with a number I know they both go into evenly because it makes it a lot easier and faster. So I'm going to go ahead and take 5x1 plus 2x2. I want to go with 10, but 10 divided by 5 is a 2. That puts us way down here. I'm going to go with a bigger number. I want to get it up over here somewhere on purpose. So instead of 10, what about 20? 5 goes into 24 times. I'm still right in the heat of things. I want to get out of the heat of things. I'm going to go with 30, right? They both go into 30. 5, 10, 25, yeah, 30. Arbitrarily, I picked a number. You can see my logic that I went through to figure out what number I would like to use. If I would have went with 10, my line would have been down here, and that's fine. Because you just need to know what angle it's at. And you got to pretend there's parallel lines next to it, all the way leading to these extreme points, wherever this ends up. If it's out here, you got to pretend you can see parallel lines leading the feasible region, whichever way you go. Again, we'll go with make a 0 here, and then we'll go with making a 0 here. If I make a 0 there, that leaves me with 2x2 equals 30. I divide both sides by 2, I get, thank you. If I put a 0 there, that makes 5x1 equals 30. I divide both sides by 5, I get 6. Here are my 2 points, 6, 0. It's going to be right there. And then 0, 15 is off the chart. Darn, that's going to ruin our angle. I think it's straight. Okay, sorry, y'all. Oh, that's awful. Okay, now we see our angle. So now we're going to take a straight edge, and this is going to be tough. And we're going to stay right on that angle. Make sure I stay parallel to that. And I'm going to head down here where the extreme points are. And since I started up in the feasible region, I need to find which one of the extreme points would be the very last one it's touching as it's leaving. And we know it's going to go past that one. Why? Look at how we're already past this one. This 5, 0 can't be the optimal solution. This is going to be smaller than 25, right? So here we go. There's that one. Am I parallel still? No, not everybody can see. It's one of these two, and because my graph is so bad, you cannot tell top one or bottom one. It is the top one. Right there, not that one. Not that one, not that one, it's that one right there. There's your optimal solution. Now you go back and you look at it and say, well, what 2 lines are crossing right there? It looks like it's this one and this one. So that is the, what is that one? Is that a 5 and a 3? Is that, no, it's not 5 and a 3. 5 and a 2, is that what it is? That's this one? No, wait. This one right here? No. Is this it right here?
Yeah.
So this one right here, if that's for sure, that's what's crossing there. And this one right here we know is this one, correct? Now, I don't remember which 2. But once you've said, I know that's now the optimal solution. And if these 2, where'd they go? We lost them. if these two right here are truly crossing right there where that optimal solution is, you just found the binding constraints. Let me repeat that. The binding constraints are the constraints that form the lines that happen to be crossing right where the optimal solution's at. And it's those binding constraints, and you could have 5, 6, 7, 8, 10 constraints here. The two that happen to be crossing right where that optimal solution is are the two you're going to use. If you remember that process I taught you the very first lecture we had starting this chapter, either the addition or the subtraction or the substitution method that then find that optimal solution with the two binding constraints. Right? Here we go. Again, we're still on review. I'm going to take these two. I should confirm these are it, shouldn't I? Just to make sure. I don't want to waste time. Let's both. Here we go. Okay, all this stuff. Let's see it. See this. Okay, all this stuff is last time. Here's the problem we did. The max 5, 7. Graphed the x1 equals 6. We graphed then the 2x1. This is the other problem that we did last week. Blah, 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 blah. Here's our objective function line, figuring out the last spot it touches. And then, I don't know, whatever it is. Oh, yeah. This first example we went over, there's those extreme points. We know one of these 5 is going to be your optimal solution. And then we found it. Here is the other one. This is the one we just did, right? And when and there's exactly putting the 0 in and getting the other numbers for all 3 constraints, right there. And then we went ahead, see what I mean by how far off this was? It should have been out here more. We have these two, and there's the extreme point, right? That top one is going to be our optimal solution. And real quick, we can see now that's for sure that third constraint, and for sure the 4 and 4. 4 and 4. That is that. No, that's not. The bottom one. So we would have wasted time. Okay, you want to see now how to calculate that optimal solution? Okay. All right. I know you guys. We'll recover. We're going to recover x1 plus x2 equals 4. Or not 4. So is it 4. All right, help me out. Do you want to use, well, you got to, you're saying that these already can cancel each other out. There's no reason to change either one. By adding them together, not subtracting, adding. Yeah, so we're not 3. Okay, 5. They cancel each other out. 16, divide both sides by 5. You get x1 equals 3.33, correct? Plug in 3.33 to either one of these. We'll go with the easy one. 3.33 plus x2 equals 4. Subtract 3.33 to both sides. You end up with x2 equals 0.67.
It's not 3.3. It's 3.2.
This is 3.2?
Yeah.
Thank you. So then, what is this right here? 0.68, right? 0.8. Subtract 3.2 from both sides. Let me get rid of that. You end up with x2 equals 0.8. Man, man. That's crazy. Here it is. You ready? These are our binding constraints. You add them together. These two are gone. You end up with 5x1. 12 plus 4 is 16. Now you can solve for x1. Divide both sides by 5. 16/5, which is 3.2. I keep thinking it's 3.3. It's 3.2. Now plug in 3.2 into either one of these for x1 and solve for x2. We're going with this one. Plug in 3.2, subtract 3.2 on both sides. x2 equals 0.8, or 4/5. There's your optimal solution. You ready? Now plug it back in to the objective function. Take the optimal solution, which is 0.8 and 3.2, and plug it back into the objective function. I know it's right there, but I want you to see it right here. Right there. So you end up with 5 times, what's x1? 3.2 plus 2 times 0.8. What you're calculating by putting the optimal solution back into the objective function, this is, not even on, this is the objective function value. Objective function value is when you plug the optimal solution back into the objective function and calculate what it equals. That's it. One last thing. Are you ready? When you have constraints other than the binding constraints, that means they were not binding. In our case, how many constraints are not binding? 1. Because our binding constraints ended up being this one and this one, I think. Who knows now? Yeah, it was. All right? So there's our non-binding constraint. Now that you have the optimal solution and you plugged it into the objective function, you have to plug the optimal solution into any of the constraints that are not binding and calculate the difference the left-hand side would be from the right-hand side. And that difference is either slack or surplus. Now, I want to make sure I have everybody's attention because nobody should ever get this wrong what I'm about to tell you. You have to tell on your quiz what you're calculating, whether it's slack or surplus. And you got to go back to the original constraint. And if the original constraint is a less than equal, it's slack, period. No matter what calculates out, it's slack if the original constraint's less than equal. If the original constraint's greater than equal, it's surplus, period. So there's no reason to get the identification one. Look right here. That faster? Right there. Have this slide to remind you, have it ready. Spot right here. Slack variables adding into less than equal slack, greater than equal surplus. So we go back to that first constraint. Out of those 3, that first constraint at the top is the one you told me is a non-binding constraint. So I'm going to plug in 3.2 and 0.8 in for x1 and x2 into that constraint and find the difference. So that ends up being 2 times, is that 3.2 or 0.8? And what's the other number? It's 2 and 5, right? Plus 5 times 0.8 equals 10. All right, 5 times 0.8, that's 4, right? And 2 times 3.2 would be 6.4. Does that sound right? Yeah. What? Plus, I add them together, I get 10.4 equals, the right side is 10. The difference between the two, 0.4 slack or surplus? Surplus, because all you got to do is look right here. And that determines whether it's slack or surplus. That's all you got to do. And because this was a greater than equal, you've got to write the word surplus. If you write slack / surplus, both of them, you're not getting it right. A lot of students will do that because they can't remember. You can't say that. It's either one or the other. It's not both. And it's either slack or surplus. And it's so easy to just look back and see if it's greater than equal or less than equal. Yeah.
So they're never equal.
Once in a while it's an equal, but you'll never have, it'll most likely be a binding constraint. You probably won't have that. Anyhow, I take that back. You ready? Remember our very first example right here, where we had, it wasn't equal. That was almost equal. If this would have been x1 equals 6, what's the optimal solution for x1 in this problem, and is it different from 6? And then would it be slack or surplus? You tell me. Whatever we find out what x1 was, and if it's different from 6, would it be slack or surplus on this problem? Slack, because it's a less than equal. And for x1, the optimal solution was, where is it? 5. x1 is 5. So do we have slack for this right here? If x1 optimal solution is a 5, it doesn't matter what x2 is 5 less, if you make 5 equal to 6, because it's not a binding constraint, how much slack do you have? 1 unit. 1 unit slack. The difference between the left side and right side, even when there's only one variable, even if that were an equal, you still put the optimal solution in and find out how far off this is from the optimal. Slack or surplus. And where you're heading is right here. Again, come on. There we go, right there. I'm on Arbiter 106. You don't have to write this page down or anything. Look at this output though. This is our next chapter that we're going to. We're not going to graph anymore. We're going to let the computer do it, or Excel. And now you tell me how much slack or surplus does constraint 2 have in this particular problem. We don't know if it's slack or surplus. We have to look back at the problem. But how much? You guys see it. See the 120? Right here's the constraints. Here are the computer outputs telling you how much slack or surplus. Now, you go back to those original constraints, these two, and you plug in 3.2 and 0.8. Each of these will give you the exact number on the left that you have on the right, because they're the binding constraints. This left side will be a 12. This left side will be a 4. And the difference between the two is 0. And the binding constraints always have no slack or surplus. So my question for you is, which constraints on this problem are binding? Julian, you said 1 and 3. Because right here, it's telling you, here's your binding constraints. Get it? And that's what you would get if you plugged in the optimal solution into these two constraints, because they're the ones forming that extreme point where the optimal solution's at. So there's a little hint. You know, slack or surplus for binding constraints is always 0. And when we get to the next chapter, you're going to have an output on the next quiz after the second quiz. Oh wait, is chapter 3 on this quiz or the next one? Next one? Yeah, you guys. Anyway, when you get to chapter 3, there's going to be an output there, just like this. And you're going to be asked questions about this, and you have to be able to identify. Now, last week, a week ago today, I showed you an output, and I said, what's the optimal solution? And I showed you where it's located. So I'm going to ask you again, what's the optimal solution for variable D? Where's the optimal solution? What is it? It's given to you right there. No. Good. I like your guess. Thank you for guessing. Anybody think? Anybody, no one remembers last week where I showed you where it's at? Wait, you're right. I'm in the parallel universe while we're all in this one right now. And in the parallel one, I mentioned it last week where it's at. But this one, I may have never mentioned it. Is that possible? The optimal solution is always the variable values at the top. So you see where S and D are? The optimal solution here, if this were all graphed out, it'd be at 540, 252. That's the optimal solution. And if we had the constraints, and we plug in 540 for S and 252 for D, they would be equal to whatever the right-hand side is, because there's no slack or surplus because it's a binding constraint. You getting this? We now know, here's the constraints, and there's slack and surplus, and how to identify binding and how much slack and surplus there is. Here's the optimal solution. Now look at the very top. If we take the optimal solution for those variables and plug it into the objective function, that's what it will calculate out to, just like we did right. Is this the objective function? Where did we do it at? Is this it? Right here? We took the optimal solution, plugged it into the objective function for the variables, and what it comes out to equal is your objective function value, which when we get to the outputs is always at the top, right there. Now, let's look at this one more time this way. Who has that PowerPoint and can go to that slide right there for me? I'm going to need you to read these numbers to me. We're going to do Excel. You ready? Somebody
Wait, I have a question.
Go.
So for back when we're finding if there's slack or surplus, so you take your optimal solution and you always plug that into the first constraint?
No. Into whichever constraints are non-binding.
is a coincidence that happens to be the first
Okay.
constraint here. But that was only because the first constraint was the non-binding constraint. That's the only reason we did that. It was the non-binding constraint, whichever constraints are the non-binding constraints.
Okay.
So on the quiz, when I'm asking you for the slack or surplus, there'll probably be an additional word that says, for the non-binding constraints. You don't have to do all of them, just the non-binding. Because the other ones won't have any slack or surplus, there's no reason. Does that answer?
Yeah, and then also,
Follow-up question.
after you find that, so they were all like facing the same way, like all the greater than and equal ones. Will they always be like that?
No, look at these. These are less than equal right here.
Yeah.
When I put the optimal solution in any of these, whichever ones are non-binding.
But like for the regular constraints, will they all be like facing the same way, or will you have less than and then greater?
No, it will be mixed. Sometimes it's mixed. Some are less than, some are greater than in problems, yes. It's just a coincidence they're all less than equal here, and it's just a coincidence that they're all greater than equal on the one we just did.
Okay. So
But it's
whichever non-binding constraint that you plug it into, depending which way that one goes, is whether
Yeah,
it's surplus.
to do slack or surplus, you have to determine which ones are non-binding. The only way to do that is to find the optimal solution.
Okay.
Then once you see that optimal solution, you're gonna go, oh, which two of these three constraints are forming that? And don't get me wrong, it's not always two constraints. It could have been one constraint crossing the axis. It could have been the extreme point that's the optimal solution. And if that happened, there'd be two non-binding constraints then, that you'd have to do slack or surplus.
Okay, so it can
But
be
it's-
different for each constraint then?
Yeah, it was this process that led us to realize that that spot right there is the optimal solution, which then led us to determine these two are our binding constraints, which then we could deduct that that other constraint's not binding, and that's the one we do slack or surplus. If you don't feel confident that you can tell which one of the constraints are non-binding, take the extra minute or two and plug in the optimal solution for every constraint, cover your bases. And find the slack or surplus for every one of them, even if it's zero, just to make sure, because I'm starting to see where some people might say, oh, this one's the non-binding constraint, and they'll plug in the optimal solution in to see if there's slack or surplus, and they'll be using the wrong constraint maybe. So to make sure you cover those points, why not find a slack or surplus for all three to make sure you're using the right constraint, in case you're not sure which ones are binding. Go ahead. Wait, did we get yours?
Yeah.
No, hers, I'm sorry, we'll come back up here.
So how do you know the difference between slack and surplus?
You gotta look at the original constraints, like this one right here is a constraint. Would this be slack or surplus? Because the original constraint has greater than equal right there. So even if this has any slack or surplus at all, it's gotta be called surplus because of that right there.
Okay.
If this left side doesn't equal the right side. Go.
Could you please repeat how to find the binding constraints and
Okay.
non-binding ones, please?
Yeah. We get all of these graphs and we shade in the direction. And then we figure out where the feasible region is because where all three shades overlap. And then you can see there's extreme points, is what they're called, that are touching the feasible region where two lines are crossing. And there's only three of them here because there's no lines crossing out here anymore. And then those 3 points, one of them is our optimal solution. And whichever one of these 3 points, or however many extreme points exist, whichever one ends up being our optimal solution, the constraints that are forming that point are the binding constraints. Let me say that again. The constraints that are forming the lines that cross at the objective function, at the optimal solution, forget the objective function, at the optimal solution are the binding constraints. The binding constraints form the optimal solution. Did they get that?
The constraints that are forming the lines that touch the optimal solution.
The lines that form the
Oh.
optimal solution. Lines that form the optimal solution are the binding constraints. The constraints that, you get it? I'm trying to say it 3 different ways, but I don't know which way to go here. Now, does everybody feel comfortable that they know where to, the objective function value, how it would be calculated? By taking the optimal solutions and plugging it in for the variables into the objective function and see what it equals. That's how you find the objective function value. forgot what I was talking about. Oh, yeah. Once you have the optimal solution, like 3.2 and 0.8, you plug that into the objective function for the variables, and what it calculates out to, 3.2 times 5, 2 times 0.8, because the objective function said 5 times x1 plus 2 times x2. What this calculates out to is your objective function value. What's 5 times 3.2? 15, 16, is that 16? Plus 2 times 0.8, 1.6. So help me if I'm, is this close?
Yeah.
Is it? Yeah. Okay, so there's our objective function value for this one. Let's check it. I think it's answering. Here's the objective function. We plugged in 3.2 and 0.8. Calculate this out. If you take 88 divided by 5, you should get 17.6. Can someone confirm that? Yes. Just confirm. So right there's how to find the objective function value, plugging the optimal solution in. All right. There's our optimal solution right there. Blah, blah, blah. Here's one. This is another way to find slack or surplus. I changed it and said, look, this got confusing for some people, and I said, let me simplify it and just say, go back to the original constraints, plug in the optimal solution, and for every variable if you need to, and see which ones are different from the right side. The ones that are not different, you just identify the binding constraints without even graphing. Once you know the optimal solution, I mean, you didn't have to find it. You could actually, well, you gotta have the optimal solution, so I don't know what to do. You ready? We're gonna use Excel now. Here we go. I just got this off of Blackboard, and those numbers are probably already on there. This is where you're entering all your data right here. This is where all the calculation takes place through Excel. So, we only have 4 minutes? Is that true? Oh, we got a half hour, right? Okay, good. All right. Who has that PowerPoint open and said they could read these numbers to me? The first constraint, the number with x1 is what? 6. The number with x2?
Oh wait, no, not in the first constraint.
Okay.
The x1 is less than or equal to 6.
No, not that one. The one we just did, the minimization, hang on, let me get rid of it.
You're talking about the one on the PowerPoint?
This one right here. So I see 2, 5, 10. I just need the numbers. 2,
Yeah,
5.
you did the example 1, so I have the example
Yeah.
1 pulled up.
You guys ready?
I'll be ready in just a second
All right.
for you. Okay.
2,
So it's 2 and 5.
2, 5. Over here, make this a 10. Now this is where you want to make your changes, not down here. Don't change any of those formulas. They're all in there ready to go for you. As long as you have 3 constraints and 2 variables, the only difference is you just copy and paste the formula, you figure out the logic if you have more constraints. You know, and then you have more numbers to enter if you have more variables. The second one has what 2 numbers?
4,
And
0,
and
12.
well, you mean 1. Negative 1, okay. And then the third constraint has what numbers? 1, 1, 4. 1, 1, 4. And then the objective function has what numbers? 5, 2. All right, that's how you do Excel. You just take the numbers off the constraints and plug them in, and take the numbers off the objective function, plug them in, make sure you have the right size correct, and then let Excel do the rest. You got to make sure you got nothing but zeros here, and this is where your objective function is at. I might as well change that to a min at this moment. Okay, and this is taking into consideration that you have 2 variables multiplied by the corresponding objective function numbers. You'd have to change this formula if you have a 3rd variable. You have numbers here and here, so you have to add, follow the logic. E10 times E14 plus F10 times F14. So if I have a 3rd variable, it'd be plus G10 times G14. Just follow the logic and add to it. So this is posted. It'll save you a ton of time just to keep using this over and over and expanding it. It says go to page 89. I'm going to try to remember. We did this last week. It's click on data. Help me out. Data solver, right? Solver? There we go. And we have the right cell locations. Is the objective function in E16? It is. Are we doing a max? No. It's a min. Changing variables. The optimal solution, remember I said put in your notes. Put in your notes, set objective, where objective function cell location is. by changing variable cells, put in your note where the optimal solution is going to be. The cell locations where the optimal solution is going to be. So in this case, I've got E14 and F14. I know you can't see the numbers. And then right here, the constraints. It's asking about these cell locations being compared to the right-hand side. So notice I got, you know what, I'm going to get rid of these constraints. I want you to see again how to enter these instead of grouping them. There. You ready? I'm going to add a constraint. That first constraint right here, that cell location, less than equal to, is that less than equal to? That's greater than equal, isn't it? Greater than equal to that cell location. Let me move this over. You ready? Here we go. Add cell reference, the left-hand side. I'm going to click right here on E20. I'm going to switch that to greater than equal, and the right-hand side to 10. Instead of hitting OK, I'm going to add a second one. The left-hand side is E21. Change that to greater than equal. All these need to be changed to greater than equal down here. The right-hand side is J21. Now I'm adding a third one. Right here, E22, hit greater than equal. The right-hand side, J22. Hit OK. And there's all three of them. E20, J20. E21, J21. E22, J22. Just so it looks good, I want, what just happened? Darn. Where did that end up just going just now? There. All right, make sure this, I'm not going to do this. Make sure this box is checked right there. When you first open this up, that box will not be checked. It's only checked because I used it already. And then this will not be on Simplex. It'll be on, I think it'll be on Mac. Switch that to Simplex LP. For all, this whole semester, this must be checked and that must be that. For the whole semester. Okay? If solved, our optimal solution will show up here. It will take these numbers times 5 and 2 and get here. We should get 17.6 right there, and these two should be 3.2 and 0.8 if this works. What happened? Okay, get it out of there. 3.2, 0.8, 17.6. Boy, this looks easy, doesn't it? This is the way to go. Once we get past this graphing stuff. Right? How do you feel about this at least? I mean, if I showed you any problem, could you know where to plug in the numbers so that it can be solved? Everyone agree with that? All right? I want to make sure you're telling me the truth. You ready? Here we go. That problem right there. Yeah. You got your camera? Someone read these numbers to me. How about this? How would I enter these numbers? I mean, I'm going to change the variables from x1 and x2 to a and b. This is the output right here. I'm going to change it to a and b. All right, here's our grid. Underneath A for the first constraint, underneath B for the first constraint. What am I putting here? What am I putting here? And then what am I putting out here? 6. There you go. Second constraint. What am I putting here? 1. And then? 1. And then 4. You're getting this. Okay. All right. I can stop there. I feel like you got it. It's the loudest you've been the whole time. I love it. I think that's the chapter. Am I forgetting anything? Let's go back to PowerPoint. Oh, our in-class is thing. We love those. What do you want? The last example is showing you one that does not have a solution. Trust me. If it's on the quiz, if it's on the final exam, it has a solution. So, you don't have to worry about something like that. Oh, you don't need to worry about something like this. The shading goes this way, this one the shading goes that way. You'll never have that. When the shadings don't overlap. When the shading doesn't overlap, there's no solution. There's no optimal solution. Okay. There's that baby one. Now, before we start the in-class, I want to talk about the homework so you guys, don't freak out when you get home. This is due in 2 days, right? 2 days. You ready? I'm giving you an objective function constraints on the homework. This isn't the in-class. You have 3 constraints, you got an objective function, you got variables x and y. Use the graphing method. Right? You draw this out however you want to do it. Use the graphing method showing all of your work. Everybody understand what I mean by all your work? Show me you're putting a 0 in and getting the other number, put a 0 in and get the other number for every constraint. Graphing your up to solve the above linear programming problem. Make sure and show the shading and include identifying the feasible region. Show me you know which way the shading goes on that graph. Put an arrow or somewhere showing me where the feasible region is. And not just arrows. Darken the lines. Like, remember our graph like this, and we have this and this and this. If the feasible region's here, you know, we can go just like this to show me that that's the feasible region. FR, how's that? You show me you know exactly where these points are. I should have put identified the extreme points. Darn. Make sure show shading and include identifying the feasible region. Include work in order to graph the objective function too. You're going to go to the objective function. You're going to decide what number to set it to. You're going to put a 0 in for x, get y, put a 0 in for y, get x. Put that line on your graph. I want to see that there's work for all these, you put that on there. Whether you took a straight edge and moved one way or another, that's up to you. There's no way of showing me that. But you've got to show me that there's a line on the graph representing that objective function. And I see work that you calculated how to make that line. Once you've identified the binding constraints, show work using one of the 3 methods taught in class to calculate the optimal solution. The subtraction method, the addition method, or substitution method, once you figure out which ones are binding. Include work showing your calculation of slack or surplus on the non-binding constraint or constraints. You know, maybe only one of these are binding because it's crossing an axis. Everybody understand what I'm expected here? What's expected? 2 days to work on it? My usual suggestion is going to be you start on it right away while this is fresh in your mind, no matter how confusing this was. Because we got a little out of place here. It will be much easier homework than if you wait. No matter how much you feel you don't understand or do understand, starting on this assignment right away is going to be the key for you. Because as soon as you walk out here, the stuff you hated the most about this, and try its best to leave your memory. It's going to try to escape when you least expect it.
So
the next song you hear is replacing it.
Since it's a max, when you're going like trying to scale it down, you want to get the first one, right? The first extreme point for the feasible region. Because what's the difference between the min and the max?
No difference at all. The min and max would be it's still you take the objective function, whether it's max or min, and you graph it, and you're looking for. Let me bring this up now. And you're looking for. The only reason I knew to go this way with this objective function line, or if it were down here to go this way, is because I knew it had to show me which one of these 3 points are the optimal solution. If I would have went this way, there's no points out there. There's this one. The objective function can't be into the feasible region. The objective function line can only touch it. So you got to say, where would this line only be touching it, and you got to stay parallel to it. And so only down here, since it's already past that one, if it went this way and it touched that one last, it's in the middle of the feasible region, so it can't be used. So the logic kind of, once you've done a couple of these, the logic starts telling you which way to go. You know,
So it's still whatever point that the line touches last.
or first, depending on your going in towards it or out of it, but it's wherever the objective function line is only touching the feasible region at one point. That one point happens to be an extreme point, and it happens to be the optimal solution. So, hang on, I'm grabbing this other one. Look at this one. All right, we know we have an extreme point here, 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 and here. We can plug 0, 0 in, and we're going to get, the objective function is going to equal 0. And since this is a max problem, we can pretty much say there's no way that should be the optimal solution. And once we figure out what the slope of the objective function is, and we go, well, let's move this way, this will be the last spot it touches. But when you plug in 0, 0, you're going to go, wait a minute, this is a max problem. It has to be one of these other ones. And all of a sudden you go, oh, I bet I got to go that way. You pass that one, You're going more, you pass that one, it's between these two. As you keep moving, and you're right there. These are just straight edges here. You're almost past that one, it's between these two, and if I kept going, you'd see that's this last little spot is touching right there. Right there. Notice the objective function line is nowhere in the feasible region. It's on the outside, just touching the last little spot. If somebody used a huge number, theirs would have been out here. They have to move in. And they're parallel to this, they get to the exact same spot this one's at, even though it went from the opposite way. Whichever way you're coming from, it will get you to the exact same spot where the optimal solution is. What works under control? All right, here we go. Braking groups, do not work alone, blah, 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 blah.